talk about quadratic functions. So, definition. Let's get straight into it. A quadratic function is a polynomial of degree 2 and its graph is called a parabola. So what do quadratics look like? It's a polynomial of degree 2. So what does that look like? Well, if we were to come up with a polynomial with degree 2 means that the highest exponent is 2. So a quadratic in standard form would look like potentially this. I'm just coming up with a random example. Right, standard form, we're decreasing the exponent of the terms as we go, and we're just adding and subtracting the terms together. They have coefficients. That's a standard form quadratic. We could also have a root form quadratic, right? We've done this before where we've had to factor something like this into something like this. These are not equal. This is just a totally separate example. But sometimes quadratics look like this. This is also root form. Look like this. Could look like even something funky like this. So they take on all shapes and forms. The thing that makes them all a quadratic is the fact that we have x squared, right? 2 x's in each one. Our first fact about quadratics: if the leading coefficient is positive, the parabola opens up. If it's negative, it opens down. So what does this mean? First of all, what is our leading coefficient again? Can we refresh on that? Our leading coefficient was the coefficient attached to the term with the highest degree, right? So in this example, our leading coefficient is 3. In this example, our leading coefficient is 2. Here we have a leading coefficient of, well, looks like nothing, but when we have nothing, it's really 1. Same thing here. And our leading coefficient here, this one's a little bit more complicated, but our leading coefficient here is still 3. Because if I was to simplify this into standard form, right, we'd end up with 3x squared as our first term because there's 2 x's. All right, so that's refresher on leading coefficient. What do parabolas look like? Well, parabolas can either, again, be facing up, right? They're these U shapes, or down. This is an up opening parabola. This is a down opening parabola. So based on our fact above, what can we say about the symbolic representation of these functions? Well, this one's up opening. We said that a parabola is going to open up if we have a positive leading coefficient. So this one has a positive leading coefficient. I'm going to shorten all those words for time. Down opening parabola means that it's negative. Okay, what else can we tell from these functions? Well, something we've talked a lot about before are maxes and mins. Each of these have a very distinct max or min, right? This point is the both absolute and local minimum of this graph. This point is both the absolute and local maximum of this graph. This point looks very similar for both graphs. This point is very special for this type of graph. It's called the vertex of the parabola. Right, so it's the minimum of an up opening parabola or the maximum of a down opening parabola. Let's write down the definition here. The vertex of a parabola is the local extremum. For an up opening parabola, it's the local minimum. For a up opening parabola, it's the local maximum. Okay, y'all, I don't know why this happened, but my phone stopped recording. So I'm just gonna talk through the things that I had written. So we have our vertex. We also have this vertical line that passes through here, which divides the function into two pieces that are symmetrical. If we fold it across this line, the two halves of the function would line up perfectly. For that reason, this line is called the axis of symmetry. Something that we might notice is that the axis of symmetry passes directly through what point on the parabola? Passes through the vertex, right? In both cases, the axis of symmetry is always going to pass through the vertex because the vertex is right in the middle of the function. So let's look at a quick example. If I was given this parabola, do we have a positive or negative leading coefficient? Well, it's opening up, so it's positive. Where is the vertex of this guy? Well, it might not be super easy to see, but we are 3 to the left, so -3 for x, and then down 2, so -2 for y. So our vertex occurs at -3, -2. Where is our axis of symmetry? Well, first of all, our axis of symmetry, again, is a vertical line. Let's draw it. We know it's going to pass straight through the vertex. So, right here. All right, vertical lines are what? X or Y equals? X, right? All of these points have the same X value. So what is that X value? What is the X value of our axis of symmetry? Well, here it's -3, right? We can see from the grid lines. But we could have also found it just from looking at the vertex, right? Our vertex passes through -3, -2, so the x is -3. Okay, let's look at the different forms of quadratic functions. This one we might recognize from general polynomials. The standard form of a quadratic is f of x equals ax squared plus bx plus c. If you'll recall from polynomials, we used, in the generic polynomial form, we had a sub n and a sub n minus 1, all the way down to a sub 1 and a sub 0. Here, we can just use ABC because we know that there's going to be at most 3. A is attached to the x squared term, B is attached to the x term, and C is the constant. Another form we'll see pretty often is root form, right? Root form of a quadratic is also similar to the polynomial form, right? We have our leading coefficient, and then we have x minus, how many roots is a quadratic going to have? Well, remember we have as many roots and factors as our degree. So if we're looking at a polynomial of degree 2, then we have 2 roots and 2 factors, R1 and R2. Now, one that we haven't seen yet is one that's sometimes called vertex form, sometimes called transformation form. This one is a little bit different. We still have that leading coefficient, but we're going to write it as x minus something called h squared plus something called k. So let's look at what the different pieces of these represent. First of all, what do all of these have in common besides x and x squared? They all start with a, right? They all start with the same leading coefficient. What else? Well, let's think about where our y-intercept is. How do we find a y-intercept, first of all? Well, it's where we intersect the y-axis, right? What is the y-axis? Well, it's a vertical line, and it's the vertical line x equals 0, right? It's all of the points where x is 0. Well, we know that the y-intercept of a function is going to have the x value 0, and then our y value is going to be whatever it is. So which one of these is going to most easily give us our y-intercept? Well, if I start at the bottom, if I plug in 0, then I have to subtract h and square it and do all this stuff. So that's not very easy. If I plug it in here, I have to subtract r1, subtract r2, and multiply everything together. If I plug in 0 here into standard form, what happens to each of my terms? Well, 0 squared times a just becomes 0. 0 times b also becomes 0. And so I'm just left with c. So my y-intercept is 0, and then the output value c. What about my x-intercept? Remember, we can have multiple x-intercepts. We can intersect the x-axis as many times as we want, but we can only intersect the y-axis once, right? We can only have one x value of 0, but we can have multiple y values of 0, right? That's a part of passing the vertical line test. So where are our x-intercepts? Well, again, these are where we intersect the x-axis, which is y equals 0. We can think of this as where is f of x equal to 0. We've talked about this before. These are our real roots, right? Our real roots can be very easily found from root form. Again, our x-intercepts are going to be points. They're going to have the y value 0, and we need to figure out what the x value is, but root form tells us directly that our roots are r1 and r2. Okay, here's an interesting one, vertex. We might take a educated guess and say that vertex is probably going to come from vertex form. I'm just going to go ahead and tell you where it shows up. Our vertex in vertex form is h and k. That's why it's called vertex form, because we can easily pull the vertex from this form, right? We can see it from h and k. We'll see why it's called transformation form and why this form is useful for us in just a second. And last but not least, what is the axis of symmetry? Where can we find that? Well, again, remember, if we know what the vertex is, then our axis of symmetry is the vertical line, so x equals, that passes through this point. So it's going to have the same x value as this point, which is h. Awesome. Okay, let's look at an example and determine all of these things for a given function. So let's say we're looking at g of x equals 2 times x plus 3 squared plus 4. Okay, so what is our leading coefficient here? Well, in each of our forms, it's always the coefficient out front. So as long as we're in one of our regular forms that we might see, we can just check for the leading coefficient out front. This leading coefficient tells us that the parabola opens up or down. Well, remember we said that if we had a positive leading coefficient, we open up. If we have a negative leading coefficient, we open down. 2 is positive, so this parabola would open up. What is our vertex? Well, it's a point. Remember, our form is x minus h and then plus k squared. A times x minus h, which is the x value of the vertex, squared plus k, which is the y value of the vertex. So remember, our form is minus h, so we kind of have to flip the sign here, right? So in this case, x is subtracting negative 3 to make it positive. So this is negative 3, we have to flip the sign, and then positive 4. And then our axis of symmetry, again, vertical lines, we have x equals. This line passes through the vertex, so the x value is going to match. Our x value is negative 3, so we have the line x equals negative 3. Okay, while we're looking at this function, let's see why we call it transformation form. You better believe it's going to have to do with graphing. I'm going to abbreviate transformation. So our steps for graphing with vertex and transformation form. Let's use this example. So again, we're looking at 2x plus 3 squared plus 4. So if we look at this, it's actually very easy for us to see what the transformations are from the basic function x squared to this graph, right? We have an addition or subtraction of something on the inside. We have some sort of vertical stretch, and we have some sort of vertical shift. So in terms of order of operations for transformations, what do we want to do first? We can start inside of the parentheses. So we have horizontal shift by h. Next, in terms of our order of operations, is multiplication, right? So we have a vertical stretch or shrink. And possibly even a flip if we have a negative leading coefficient. By A. And then, last but not least, we have our addition on the outside. Addition on the outside is a vertical shift. By K. So let's do that with this one. So remember, we're initially starting with our regular old graph of x squared and transforming that guy. So that looks like this. So this is kind of step 0. We want to start with x squared. Our first step is to shift horizontally by h. We have a +3, which means that we move left by 3. So we have 1, 2, 3 to the left. So our new vertex is going to move from being at 0, 0 to -3, 0. And our graph kind of goes like this and like this. So this is step 1. We've shifted here. Now we have our vertical stretch or shrink or flip, but what is it here? Well, it's a +2, which means that it's a vertical stretch. So each point is going to be about twice as tall as it was before. So looking like this, it's very skinny and very tall. So this is step 2. And then our last step is our vertical shift by K. We are shifting 4 up. So we have 1, 2, 3, 4 up. Our new vertex is here. And so our final graph, we want to keep up that kind of stretch. This is our final one. So one thing I'd like for us to notice is where our vertex has shifted to. Remember, our horizontal transformations are going to take us in the opposite direction of where we think they're going to go, right? So +3, we might think that we're moving to the right 3, but we're actually moving to the left 3, right? So we move to -3, and then we've moved up 4. So this point is -3, 4, which is exactly what we said our vertex was going to be. So first of all, that's why we have to flip the sign of h, because we're moving in the opposite direction. And then second of all, that's why this is called both vertex and transformation form, and how we can find both from this form. Let's look at how we can translate between the different forms. So going from vertex to standard form, is pretty simple. We're kind of just simplifying. So all we need to do is FOIL, right? Multiply out x minus h squared. Then we distribute a, which is our leading coefficient, and we add k. Easy as that, right? This is just simplifying. So g of x is 2 times x plus 3 squared plus 4. Again, let's look at the same example. So remember, we're just simplifying. So let's go ahead and FOIL out this x plus 3 times x plus 3. So that leaves us with 2 times x squared plus 3x, which is 6x, plus 9, all plus 4. We distribute the 2 to every term. We get 2x squared plus 12x plus 18 plus 4. And then we add on that plus 4, and we're left with 2x squared plus 12x plus 22. How do we convert between standard form and vertex form? The formal process of doing this is actually something called completing the square. We're not actually going to talk about how to complete the square here. We're going to do sort of a shortcut, but completing the square is something you might see if you continue on to later math classes. Again, this is a shortcut. If anything you see in this class asks you to complete the square, you can take this shortcut. The nice thing is that it's a shortcut. The not nice thing is that it means we have to memorize some stuff. I don't love asking y'all to memorize things, but we have to do that here, unfortunately. So the first step is to find h by computing negative b over 2a. Then using that h value to find k. How can we find k? Well, we know that k is the y value on the function at the x value h, right? So how do we find the y value of something at a certain x value? We plug it in, right? So we find f of h, and that will give us k. So then we'll have h and k from our formula. All that's left is the leading coefficient, but remember that our leading coefficients are the same, so we can just pull a from standard form. So then we can take all of those h, k, and a into our vertex form. So let's give this a shot. Let's say we're starting with, let's use a different function this time. So we have f of x is x squared plus 6x plus 2. All right, our first step is to find h. We need to use our little formula, which is negative b over 2a. What is b here? Well, remember, a was our coefficient of our x squared term, b is our coefficient of our x term, so b is 6. So we have negative b, negative 6, over 2 times a. What's the coefficient of a? It's 1, right? So we simplify this, we have negative 6 divided by 2 times 1. 2 times 1 is 2. Negative 6 divided by 2 is negative 3. So we have the x value of our vertex. In order to find the y value, we just plug it back into our function. So we look for f of negative 3. We've got negative 3 squared plus 6 times negative 3 plus 2. This gives us 9 minus 18 plus 2. We get negative 9 plus 2 gives me negative 7. So that means that our vertex is negative 3, negative 7. So that's how we can find our vertex. if we look at our vertex form, we've got a x minus h squared plus k. We've found h and k, we just need a, but remember, a is the same as the leading coefficient from our original function. What is our leading coefficient here? It's just 1, right? So vertex form of f of x is 1 times x minus h is negative 3 squared minus k, so we have minus 7. If we want to, we can simplify. We end up with, we don't have to write the 1, x plus 3 squared minus 7. That's the answer. Okay, now that we know how to do this, let's look at an example in the lab manual. This is from the Quadratic Functions section of the lab manual. Let's look at this number 1 here. So it's asking us to determine the vertex, direction of opening, a max or min, and the transformation form of the function. Well, we have to find the vertex on our way to finding the transformation form of the function. So let's work on finding the transformation form of the function, and it'll give us the vertex. So h, here, again, our formula is negative b over 2a. b here is negative 6, so we have negative 6 divided by 2 times a is 2. Negative 6 is 6 over 2 times 2 is 4. 6 divided by 4 is 3/2 or 1.5. I'm writing it as a decimal because it terminates, right? It's not a decimal that continues forever, so there's no rounding involved, so I'm going to write it as a decimal, and it's still an exact answer. K is the value of the function at h. We can find that by plugging in h for x. H we said was 1.5. So we have 2 times 1.5 squared minus 6 times 1.5 plus 9. 1.5 squared is 2.25 times 2 is 4.5. So this is 4.5 minus 6 times 1.5 is 9. And then we're adding 9. So in total, we end up with 4.5. So we have our x value and our y value of our vertex, which means that our vertex is, we can go ahead and write it. H is 1.5, k is 4.5. So we've found the vertex. Let's go ahead and write the transformation form of the function because we're pretty close already. All we have left to find is a, but we can find it by just looking at the function. A is the coefficient of our x squared, and it's 2. So vertex form of the function is leading coefficient, 2, times x minus h, which is 1.5, squared, plus k, which is 4.5. That's our transformation form. So that's done. We want to find the direction of opening, up or down. We can do that by looking at A. Again, A is 2, and because 2 is positive, that means that we're opening up. So opens up. It asks for the max or min. Well, we know that the max or min is going to come from our vertex, right? We know that the function opens up. So if it's opening up, are we going to have a maximum or a minimum value? If it's opening up, then it's continuing upwards forever. So we're going to have a minimum. What is our minimum? Our minimum value. Remember, max and min are y values, right? They're vertical. We're looking at the smallest point vertically. So our minimum is the y value of the vertex, which is 4.5. Okay, what about converting from root form to standard form? So this is similar to converting from vertex to standard form. We just want to FOIL x minus r1 times x minus r2 and distribute the leading coefficient, a. Again, we're kind of just simplifying. We've done this a bunch before with quadratics, we just haven't necessarily called it converting from root to standard form. Now, converting from standard to root form is interesting. If we think about it, this is actually how we find the x-intercepts of a function that's in standard form, right? Because the roots will give us our roots, which are our x-intercepts. So converting from standard to root form is actually just factoring. We've had to do this before. For instance, let's say that we started off with something like this. Minus 10. Well, we would factor. Each of these terms is divisible by 2, so let's factor out our leading coefficient. We end up with x squared. We've got, if we divide 8 by 2, we have 4 left over. If we divide 10 by 2, we have 5 left over. We factor this either by using the grouping method or trying to think about what adds together to give me positive 4, multiplies to give me negative 5. Sounds like x plus 5, x minus 1. This is root form, right? This is my leading coefficient. 2 is my leading coefficient, and my roots are negative 5 and 1, right? Because we have x minus our roots. We can also find them by setting them equal to 0 and solving, right? So we have x equals negative 5 and x equals 1. Again, when thinking about the fact that we're finding our x-intercepts here, our x-intercepts are where we're intersecting the x-axis, right? Or where we're equal to 0, where we have the output of 0. In order to figure out where a quadratic is equal to 0, just like when we had to do this when we were finding the domain of rational functions with quadratics in the denominator, we have to factor, right, and set each piece equal to 0 and solve. So we are finding our roots by converting to root form. Sometimes it'll ask for the roots in point form. We would just give them like this. Okay, so this is really nice, but what happens when we don't have such a nice function? What happens if we can't factor? We have a very nice formula. I'm kind of joking when I say nice. Called the quadratic formula. It looks like this. There's a song that goes along with this. I'm not going to sing it, but you can look it up on the internet. We have x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. I know it's a kind of long formula and it is kind of annoying, but we do want to get to know it now. The sooner you memorize it, the easier it'll be. We're going to see the quadratic formula throughout the rest of the semester, so the sooner the better. So how can we use the quadratic formula? Let's look at a function that we can't factor, like this guy. And let's say I asked you to find the x-intercepts. To find the x-intercepts, we're looking for where f of x equals 0. So if we want this to be 0, we're looking for this, right? The quadratic formula is going to give us the x-intercepts. It's going to give us the roots of the function. So first of all, what is a, b, and c? A here is 1, right? It's always attached to the x squared. B here is 4, always attached to the x. And c is negative 2, the constant term. We take each of these guys and we plug it directly into the formula. So again, we have negative b. B is 4, so negative 4, plus or minus the square root of 4 squared minus 4 times a is 1, c is negative 2, all over 2 times a is 1. All right, and then we can kind of start to simplify. So we have negative 4 plus or minus the square root of 4 squared is 16, minus 4 times 1 times negative 2, that's actually plus 8, right? Divided by 2. We add what's underneath the radical together. We get the square root of 24 all over 2. We plug this into our calculator. We have to be very careful with our parentheses because we want the stuff on top to all be divided by 2, which means we need parentheses on top. When I add the square root of 24, I get 0.449. And when I do the same thing, but I subtract the square root of 24, I get negative 4.449. That's what plus or minus does. It means I want to both add the square root of 24 and subtract the square root of 24. So this guy is negative 4 plus the square root of 24 divided by 2. And this guy is negative 4 minus the square root of 24 divided by 2. These are my x-intercepts. Now, if I wanted to write this function in root form, I would write it like this. So we have f of x. Our leading coefficient is 1, so we don't have that guy. I'm going to write it in exact form. It's pretty ugly, but exact form would look like this. Right, exact form is where we don't round. So because this has some major rounding, we have to write it in this way. So we have x minus one of the roots and x minus the other root. So this is the function in root form. Let's look at an example that simplifies a little bit nicer, but helps us kind of illustrate what's going on here. So let's look at f of x equals x squared plus 4x minus 5. Again, let's find our x-intercepts. So if I plug it into the formula, I have x equals negative b. B is 4 here, plus or minus the square root of 4 squared minus 4 times a is 1 times c is negative 5, all divided by 2 times 1. I go ahead and simplify. I have negative 4 plus or minus square root of 16 minus 4 times minus 5. Negative 4 times negative 5 is 20. All divided by 2. I end up with negative 4 plus or minus the square root of 36 divided by 2. What is the square root of 36? Well, it's positive and negative 6, right? We've got this plus or minus here already. So we have negative 4 plus or minus 6 divided by 2. What does this equal? Well, again, we have negative 4 plus 6 divided by 2, and also negative 4 minus 6 divided by 2. Which means we've got negative 4 plus 6 is 2 divided by 2. And also negative 4 minus 6 is negative 10 divided by 2. So we end up with 1 and negative 5. That means that our roots are 1, 0 and negative 5, 0. What if I'd asked y'all to find the roots from this form here without using the quadratic formula? Well, we would set the whole function equal to 0, right? When we have a quadratic function that's equal to 0, we have to factor. This factors into, you've actually seen this recently, right? Positive 5 and negative 1. We solve each of these, we end up with x equals negative 5 and x equals 1. So we get the same thing both ways. But quadratic formula works when we can't factor, unlike this method, which we need to be able to factor. All right, let's find the x-intercepts of a couple of functions in the lab manual. Let's say we're looking at 1 here. So we want to plug into our formula. Our formula is negative b. So negative b is negative 2 plus or minus the square root of b. Again, b is negative 2. We want to put that negative inside of the parentheses. If we don't do that, it's going to mess us up. So we have negative 2 squared minus 4 times a, so negative 3, times c, positive 3. And all of that is going to be divided by 2 times, again, a is negative 3. So we have negative 2. That gives me positive 2, plus or minus the square root of negative 2 squared is negative 2 times negative 2, which is positive 4. Minus 4 times negative 3 times 3 is, well, 12 times 3, which is positive 36. Must have made this too long. All divided by 2 times negative 3, which is negative 6. So we have 2 plus or minus the square root of 4 plus 36 gives us 40. All divided by negative 6 gives me, let's plug this into our calculator. Again, we need everything in the numerator to be on top, so we need parentheses. We have 2 plus the square root of 40 divided by negative 6. So we get negative 1.387. And we also want to do 2 minus the square root of 40 divided by negative 6. And we get 0.721. It asks us to check our answers using Desmos. We can plug this in, we can type this function into Desmos. We look at both x-intercepts, and we see that there, on the left side, we have a point that's between negative 2 and negative 1. Looks like it's probably negative 1.387. And then on the right side, we have a point that's between 0 and 1. Looks like it's probably pretty close to 0.7, so we are correct. On the next page of the lab manual, it asks us to find the equation of a function given the graph. We know how to do this with polynomials. We've been doing this already. Let's look at an example of it with a quadratic in particular. So this is going to ask us for both transformation form or standard form. And just for fun, let's also write it in root form as well. I'm actually going to do this one in our notes so that there's enough space to write this one out. This is number 1 under practice under part 3. So we're given this graph, and we're asked to first write the equation in transformation form, which we also know as vertex form, which means we're going to use the vertex. The vertex here is, well, it's that lowest point right at the bottom. It's 0.2 and then negative 3.2. So we have f of x equals a times x minus h, which is the x value of our vertex, 0.2 squared, and then plus k. K is the y value of our vertex, so we end up with minus 3.2. All right, so we're left with a, which we need to find here. How have we found a in the past? How have we found our leading coefficient in the past? Well, when we had polynomials, when we were writing the equations of polynomials given the graph, we needed to solve for a as well, so we got rid of all of the other variables. So we could plug something in for x and y. Let's do that here. We've got 2 points that are marked that are not our vertex. Let's use 1, 0 and see what happens. So if I plug in 1, 0, my x value is 1. I've got 1 minus 0.2 squared minus 3.2. I end up with 0 equals a times 0.8 squared minus 3.2. All right, how do I get the a by itself? I need to add this 3.2 to both sides. So I end up with 3.2 equals a times 0.8 squared. This means that a is 3.2 divided by 0.8 squared, which is actually 5. So that means that my whole function altogether is 5x minus 0.2 squared minus 3.2. This is vertex or transformation form. All right, next it asks us to write it in standard form. Remember, we can convert from transformation to standard form by just simplifying, right? So if I simplify this, I first start out by FOILing here. So x minus 0.2 squared is the same thing as x minus 0.2 times x minus 0.2. I multiply the first 2 terms together, I get x squared. I add the outside terms, so negative 0.2x, to the inside terms, minus 0.2x. So we end up with minus 0.4x. And then 0.2, so we have 5x squared minus 2x, and then positive 0.2 minus 3.2 gives me negative 3. So this is the equation in standard form. And last but not least, I know it doesn't ask us for this, but I would like for us to find this function in root form. We totally know how to do this because we know how to find the equation of polynomials from a graph, and a quadratic is a polynomial. Remember, root form is our leading coefficient times x minus each of the roots. So our leading coefficient we already know is 5. And then our roots, if we look at the graph, we have one root on the left at negative 0.6. It's passing straight through the x-axis, so it has a multiplicity of 1. So we have x minus negative 0.6, so plus 0.6. And then on the right side, we have a root at 1. Again, the function is passing straight through it, so we have a multiplicity of 1. So we have x minus 1. And this is root form. So again, this is transformation or vertex form. This is standard form. And this is root form. Okay, sometimes one of these is going to be easier to find than others. So if you're given a choice, you can choose wisely. Sometimes they'll ask you for a specific one. You'll just have to read the instructions for whatever problem you're looking at. Okay, I know that was a big lesson, but that's the end. Thank you guys for watching.